this
family,
session.
they are believing that you did it.
Amavasya vitta, Amavasya vitta, ಅದಕ್ಕೆ.
They are celebrating.
Alright, we'll now start with the introduction before understanding the basic history. So all the technology started growing with the invention of transistor by Shockley, Brittain and Bardeen in Bell Laboratories, and after that in the year 1961, that is in the early 60s, IC was first introduced. So IC was introduced, and at the same time integrations, different levels of integrations. And the different levels of integrations, as all of us know in the basic classes we have studied this, is the small scale integration where 10 to 100 transistors are used in the construction of IC, and finally they end up with a device called as logic gate. So this was in the year 1960s, and 5-6 years later the second stage of integration improved, with the number of components being placed on the IC increased from 10 to 100 to 100 to 1000 components, or 1000 different components, not only transistors, alike transistors, different components. And that was called as the MSI, or medium scale integration. And using this technology, a device called as counters were developed. So this belonged to the second generation of integration, which is medium scale integration. And next we have large scale integration, or LSI, where the components fabricated on a common platform is around 1000 to 20,000 components. And finally we have an 8-bit chip, or an 8-bit microprocessor. So early 84, this was the 8-bit processor, and this was devised or designed using LSI, large scale integration technique. And eventually components, more number of components were fabricated, and it was from 20,000 to almost 10 lakh components, and that category was known to be as VLSI, or very large scale integration. And using this technique, which is currently running, therefore using this technique we have almost 16 to 32-bit microprocessors. So 8051, 8086, they all belong to this category of processors, and this is what has been devised. And next, larger than this is the ULSI, or the ultra large scale integration, which is around 10 lakh to 100 lakh components, and the devices are almost used in artificial intelligence, virtual machines, or space applications. So there are special processors, smart sensors like this. So this is where technology has taken. And apart from this, the next generation was, though it is not mentioned here, it is called as the giant scale integration, GSI, where advanced, all completely, this itself is virtual, so giant scale also is considered as virtual. And this is where most of the techniques are involved, and research is strongly going on in this technique, or in this particular field. So this growth of technology, or the different generations, is based on a law called as Moore's law. So what is the definition of Moore's law? Moore is nothing, he is none other than a person called as Gordon Moore, who is the pioneer in finding out, or the founder member of this company called as Intel Corp. So in the year 1960s or early 60s, he predicted a statement, and that got to be called as Moore's law. So what is the definition of Moore's law? The number of transistors embedded on a chip, that is the number of components you are placing on a chip, doubles after every 1.5 years, or 18 months. So after every 18 months, the number of components you are going to fabricate in an IC would double. This was the prediction given by Moore's law, and you can see this is how the Moore's law graph goes on. It is completely in accordance with the law predicted, and it is very much linear. So till the year 2010, approximately 2000 and 2010, there is no much change. almost it is linear. It's only after 2010 onwards it is saturated and there is no more growth. So this is how the Moore's law prediction goes on. The number of transistors is taken on the y-axis and the years is taken on the x-axis. So this diagram shows the speed in megahertz. Along with that, the speed also has been shown here, and the graph given in figure also shows the variation of speed of the chip in megahertz. So this is another diagram which I will be shortly telling you. So this is in accordance with the Moore's law definition. And looking into this, we have a different graph which depicts different techniques or different families. So you have CMOS here, you have BiCMOS, you have ECL, emitter coupled logic, you have NMOS, and you have GaAs, gallium arsenide. So when you look into this, you have different technology or different families or technologies indeed. And what you see on the x-axis, so you have the power dissipation on the x-axis and speed on the y-axis. When you see here, the power is indicated in terms of watts. Therefore, if you see near the origin, it is in microwatts, 10 microwatts, 100 microwatts, 1 milliwatt, 10 milliwatt, and 100 milliwatts. So if you look into this, this is the power dissipation, and what is it you notice? CMOS, if you look, it is lying in the range of microwatts. CMOS is lying in the range of microwatts. You have BiCMOS lying from microwatts to milliwatts. So power dissipation is more. If you see emitter coupled logic, it is in 10 milliwatts to 100 milliwatts, even much more dissipation. So what is the advantage? Which one is considered as the best one? If you look into this, gallium arsenide could be considered, but still it is also reaching the range of 1 milliwatts. NMOS is also in milliwatts. So apt here is the CMOS one, which is in the range of microwatts. And similarly, when you consider the speed, you have the speed in terms of microseconds, and finally you have it in picoseconds. So when you look into this, CMOS is not that good enough in terms of speed. It is in the range of microseconds, but the best one, if you notice, you have the gallium arsenide, which is in terms of picoseconds. But in terms of power dissipation, it is not having the best feature. So when you look in terms of power dissipation, CMOS is best. When you look in terms of speed propagation, gallium arsenide, BiCMOS, they are all better. They are all better than CMOS. So most, for some reasons, these two are not, because BiCMOS is bulky. Gallium arsenide is also little more complicated in fabricating that kind of a transistor. The best in all ways is the CMOS. Therefore, CMOS is the best one considered in terms of power dissipation and appropriate speed propagation. Therefore, we will understand CMOS in detail. So, classification of transistors. As we all know, very much all of you are familiar with BJT, bijunction transistor. You should also be aware of the other device called as FET, which is field effect transistor. Both are in fact transistors itself, but the differences we will gradually get to know about them. Different types of BJT are familiar ones are NPN and PNP. Only two types, which is nothing but a two junction device, BJT, bijunction. Therefore, NP is one junction, PN is one junction. Similarly, PN and NP here. Whereas in FET, you have two types, which is called as the JFET, junction field effect transistor, and the other one is MOSFET, metal oxide semiconductor field effect transistor. And in JFET, you have two types, N channel and P channel. As and when time arises, let me tell you the difference between N channel and P channel. In MOSFET also, you have depletion MOSFET and enhancement MOSFET. So please understand, in depletion mode, there is a channel. Channel exists during fabrication itself. In enhancement, there is no channel. By the application of the voltage, a channel is induced or a channel is created. So enhancement channel will not have a Enhancement device will not have a channel. We have to create a channel by giving appropriate voltages. And the two types are N channel and P channel.